All right, so now we're going to talk about a new class of numerical methods for solving initial value problems. So right up to now, we've been studying what are called one-step methods. So what one-step methods are, in essence, are that they're methods which only rely on you having access to the kind of information it's like you need. It's like to set up the initial value problem, which is the vector field that's like and the initial condition. Okay, with multi-step methods, what you'll find is that it requires some additional information as well. Okay, so these are what are called multi-step methods. And these are in contrast to the two classes of one-step methods which we studied, which are the Taylor method and the Runge-Kutta methods. So up to now, right, we have considered what are called one-step methods. Such as the Taylor method, and the Runge-Kutta methods. And the main point is that it only relies on you knowing the initial condition, right? Sort of knowledge of the initial condition. And the vector field, obviously, right? Okay, so so the idea then is that after you've taken a few steps of these one-step methods, then you have some approximation of the solution. It's like at a bunch of different points. And you can ask yourself, well, given that information, can we, instead of doing what we do, it's like with a high-order one-step method, which is compute a whole bunch of things which allow us to approximate essentially the derivatives of the solution, it's like at a particular point, can we do something different instead, which takes advantage of the fact that we happen to know the solution values at a bunch of different points, right? So, so by the time sort of we've taken sort of k steps, all right, in using one of our one-step methods. Right, we have computed approximations. At sort of time t0 all the way up to tk, right? So, so the question is, can we use this? Well, let's see. The approximations obviously are y0 all the way up to yk at times t0 to tk, right? Can we use this, right, to compute yk plus 1 to a high order, right? Okay, so let's think about that. And as was the case with the Runge-Kutta methods, it's what essentially happened was that we weaponized the fundamental theorem of calculus. So let's try to see whether we can do something similar there again, right? So we know that there's a differential equation, y dot is equal to f of t, y of t, right? Okay, and so by the fundamental theorem of calculus, yk tk plus 1 is equal to y at tk plus the integral from tk to tk plus 1 of f let's call the dummy variable s, then f of s y of s ds, right? Okay, and let's think about what's happening here, right? We know y at time tk, and we want to figure out what it is at time tk plus 1, at tk minus 1, and so on, right? All right, so what we can do, right, is, and we're trying to evaluate f at k and f at k minus 1, right? And then we're trying to evaluate the integral. So this, let's just say, is f of t y of t, right? That's the curve which we are trying to compute the integral of from tk to tk plus 1. That's the expression here, right? And we know the fk's at, we know the f's, it's like at the previous times, right? So what you might expect to do, what you might expect to do is to fit a polynomial, it's like, to the data which you already have from the previous times. And then it's like that gives you a polynomial which you can then integrate over the interval tk to tk plus 1 to give you an approximation of this integral. Okay, so the idea, right, is to fit a polynomial to the sort of fk minus 1 and so on, and then use this to construct an approximation of this integral from tk to tk plus 1 of fs ys ds, right? Okay, so let's try to go ahead and do that. Okay, so let p m minus 1 of s, right, be the m minus first degree sort of polynomial that interpolates f tk yk all the way up to f tk minus m plus 1 yk k minus m plus 1. Okay, where your yk obviously is an approximation of y at tk, and so on. All right, so so I can write down, it's like the Lagrange form of the interpolating polynomial for this, right, which we've done before. It's like when we were deriving Newton-Cotes type formulas. Okay, so the Lagrange form of the interpolating of the interplant is the following, right? Okay, sorry. So that's p m minus 1 of s is the sum from L equals to 0 to m minus 1 of the Lagrange polynomial, right? This is the product from j equals to 0 to m minus 1, j not equal to L of s minus tk minus j over tk minus L minus tk minus j. All right, and then f evaluated at tk minus L, y k minus L. All right. Okay. So once you have that, obviously you can compute the integral, right? right? So you can have that yk plus 1 is equal to yk plus the integral from tk to tk plus 1 of this polynomial pm minus 1s ds. All right. Okay, so this is the part which depends on s. We can integrate that from the interval tk to tk plus 1 to get some sort of coefficient, and then this is the f value. Okay, so what's going to happen when the dust settles is that this is going to look like yk plus h times the sum from L equals to 0 to m minus 1 bl f tk minus L yk minus L. All right. And I'll write down what BL is. Where BL, right, is equal to the integral from tk to tk plus 1 of the Lagrange polynomial, right, product j not equal to 0, j equals to 0 to m minus 1, j not equal to L of s minus tk minus j over tk minus L minus tk minus j. All right, ds. Okay. All right, so if you do this, it's like this leads to what are called the m-step Adams-Bashford method. This yields the sort of m-step Adams-Bashford method. Okay, so so again, it's like in order to use this method, you need to know not just the function, not just the solution at the initial time, but sort of the previous times as well, right? So in order to use this method, right, we need to know y at time 0. At time t0, it's like y1 all the way up to y at m minus 1, right? Y at tm minus 1. Okay. So the basic idea then is that actually in order to use one of these Adams-Bashford methods, which is an example of what we call a multi-step method, right? You need to pair this, it's like with a one-step method of comparable order of accuracy, like a Runge-Kutta method or a Taylor method, so that you can generate, it's like this initial set of approximations of the solution. And then once you have that, you can then use the these multi-step methods. So you might then ask, well, what is the motivation for using a multi-step method if you have to pair it already with a one-step method? And the reason, of course, is that what you will oftentimes see is that once you've started up, it's like the multi-step method, then the additional cost of computing new iterates of the method is much cheaper. It requires far fewer function evaluations in order to achieve the same order of accuracy as compared to, say, a Runge-Kutta method. And the reason, of course, is that with a Runge-Kutta method, you've thrown away all this data, and so in order to get a high-order approximation of the solution of the initial value problem, you have to compute all these internal stages so that you can, it's like you can generate enough information, it's like of the vector field to be able to construct a high-order approximation of the solution. Whereas with the multi-step methods, you take advantage of the function evaluations you've already done in the previous steps to construct this similarly high-order similarly high-order approximation of the solution. So you require, again, far fewer evaluations of the vector field in order to get this method to work. So as an example, if you look here, right, you have this method that says that, oh, the solution at new time is the solution at the old time plus some, again, weighted combination of the function evaluations. But again, the thing to realize here is that you've already computed, it's like most of those function evaluations. So the additional cost of doing this is of the order, in this case, well, it's actually just one additional function evaluation per step. Whereas if you try to do this with a Runge-Kutta method instead, it's like you would require much more function evaluations to get the same order of accuracy. Okay, so let me just stop here, and then it's like the next thing I'll do is talk about an example of these sort of Adams-Bashford methods. So let me just stop here for a minute.